My name is Luzzi, and today we'll be talking about landing humans on Mars, and particularly about how important it is to characterize resources, local resources at the landing site, and of course also safety measures. Let's start our journey. Okay. So our species started to migrate actually almost 2 million years ago. So it's been a long time since our ancestors first decided to move to look for a better place, coming to resources. But I think that in addition to the need of water, in addition to the need of resources for tools and to build weapons or whatever they needed to build, I like to think that there was also at least a minor component of curiosity when they were exploring new worlds, new places on our globe. And we arrived to nowadays where we are not just exploring new places on our globe, but we want to see what's beyond our globe. So we're going to explore new worlds. I put this quote here because I really like this, and I think it has to make us think about it. It's from a Challenger astronaut Onizuka, and it says, "Every generation has the obligation to free men's minds for a look at new worlds, to look out from a higher plateau than the last generation." So the last generation was basically our parents' generation, and they saw the first man on the moon. And I'm a bit optimistic, I've been told, but I really think that in our lifespan, we will be able to see the first man on Mars. So we're very lucky to be alive in this moment where the technology advancements are getting us closer and closer to sending the first human settlements to Mars. But how will we do that? So the most important thing, I believe, is technology. So here on the left, you have an image with a few space vehicles. We have the Saturn V, who brought the man to the moon in the 70s. And after Saturn V, there haven't been really huge advancements in technology when it comes to vehicles, space vehicles. Up until now, when there is this Starship vehicle built by the SpaceX company, which is truly, really game-changing. And why is that? Well, because for the first time in history, we have a fully reusable vehicle. And it makes total sense because until now, for every launch, we were basically wasting a rocket. We were just using it once and then throwing it away, throwing away money and resources for that vehicle. But now with the Starship, we are able to land and then start again, filling the fuel. But we're not just wasting a vehicle for every launch. And this is huge. And it also means that missions are going to be much cheaper compared to the previous missions. Now, for example, let's take Curiosity, the rover on Mars. To launch Curiosity, we spent $243 million, which means about $100,000 per pound, which is a lot. With the Starship vehicle, we can launch the very same rover just for $900 per pound. It's a huge difference, and that means that we can open up space to more people, to more missions. It's going to be cheaper. And also another very important characteristic of the Starship is the increased payload, because we can send several Curiosity rovers just in one Starship. It's really, really huge. It's so big that we can fit even heavy construction machinery on a Starship to build a base that is not just for a few people, but it's basically a citadel. So in this image here from SpaceX, this is what SpaceX is envisioning. So really a small city on Mars with all specialists and scientists and engineers. And it's something really that I think it was not imaginable some decades ago. So in addition to the technology, we also need a timeline that can ensure the safety of the human beings, right? So the idea is to first send an uncrewed Starship, and its payload will be composed of everything we need to build the base. So materials and the heavy construction machinery and whatever we need to build this base. So this first Starship will leave the atmosphere and will go into orbit. Now, as you all know, gravity on Earth is pretty strong, so most of the fuel is going to be spent just to exit our atmosphere. And that's why a second Starship with a payload made entirely of fuel will reach the other one into orbit that will dock, and we will refill the fuel. And from that moment on, you have a fresh start. And the first Starship can finally start off the long journey to Mars. And then once this Starship lands, we have to make sure that everything is safe for human beings to go there. We cannot land humans without being sure, A, that the landing is safe, so the surface can bear the touchdown. And also the second thing we have to make sure is that there are no signs of life. So is there life on Mars? This is the huge question of the scientific community. We don't know yet. So far, it seems we haven't found evidence, but there might be life. And I'm not talking, of course, dinosaurs or aliens. I'm talking bacteria, small organisms. But even though these organisms might be small, they could still be dangerous for the human crew. So we have to make sure that there are no signs of life at the landing site. And at the same time, also humans can be dangerous for any form of life. So we need to make sure of that. And after we're sure that landing is safe, we can send the second Starship with the human crew. And from that moment on, everything starts, everything is put in motion. So we have to start build the base. And most importantly, we have to enable as soon as possible in situ resource utilization. So in situ resource utilization, which basically means living off the land, is crucial. Because we cannot rely on Earth. It's not like we can ask for, a package delivered by Amazon for every need we have. So we need to make sure that we have enough water, enough food, and enough resources to stay there, to have a self-sustained human settlement on Mars. So there are many resources that can be extracted and used on any planet or satellite or whatever, but the most important for human exploration, of course, is water, because we need water to function as human beings. We also need oxygen, and we need water also to produce propellant. So it's of the utmost importance, characterizing the water ice available nearby the landing site and understand the best way to extract it and use it. So we cannot go there and just try and start drilling and see, oh, maybe here we can find some ice. No, we have to know in advance, where is this ice, how deep it is, and also the composition. Is it pure ice or not? So here on the left, we have a sketch of Otto Gopher, because technology is advancing in many ways towards this direction. And this particular instrument basically drills into the rock, so it breaks the rocks, and then when it gets to the desired depth, it collects a sample. And it's very important to protect this sample because it cannot get in contact with the Martian atmosphere, because on Mars, sublimation is a beast, and we don't want our eyes to be in contact with the atmosphere. So this is more on the engineering point of view, and I'm not an engineer. So I will talk about how you can choose a good landing site and what are the conditions that need to be met. So for human exploration, particularly, there are two things that we really, really need. One is accessible near surface ice, as I said before, for in situ resource utilization. And this would drive us towards polar regions, right? At the same time, we also need solar illumination and a benign thermal regime, and these would drive us towards the equator. So the mid-latitudes represent the best solution to maximize both the occurrence of near-surface ice, but at the same time also having a good solar illumination and satisfying all the thermal requirements. And then in addition to these, we also have some safety conditions that need to be met at the landing site. So the elevation of the landing site has to be preferably minor than -3 kilometers compared to the homology. And why is that? Because we want to encounter as much atmosphere as possible during descent to slow down the vehicle. And at the same time, we cannot land on steep cliffs, for instance, right? So we want slopes to be minor than 5 degrees over a 10-meter length scale. And also, we don't want to impact huge rocks. So we need an area where rocks with a diameter greater than 1 meter are not so common. Also, the surface of the landing site has to be radar reflective, because during descent, we want to measure the distance to the ground. We want this control. And of course, last but not least, the landing site surface has to be load bearing to support the touchdown. So we're not going to choose an area where, for instance, we can hypothesize that there are caves underground, right? So it has to be a load bearing surface. Now, Golombek et al. In 2021 considered all these conditions that I just listed, and they came up with a down selection of candidate landing sites. And these landing sites are in Flegra Montes, Erebus Montes, and Arcadia Planitia. So all these 3 regions are at the mid-latitudes, and they all show evidence for near-surface ice, abundant near-surface ice. But as the name suggests, and also this elevation map, in Flegra Montes and Erebus Montes, we have some positive reliefs, and reliefs that are not consistent with the safety we're looking for. So Arcadia Planitia represents the best candidate because it's super flat and smooth and safe. And in addition to that, it's also at the mid-latitudes, and we have evidence for ice. And that's why in our project, we're working on Arcadia Planitia. In Arcadia Planitia, multiple authors found evidence for near-surface ice, and they did so through independent data sets. They all came to the same conclusion. So they used neutron spectrometers, a gamma ray spectrometer, radar data, of course, thermal emission imagery, and also imagery, high-resolution imagery to study the geomorphology of the areas, because there are also some geomorphological clues pointing out to occurrence of buried ice. Now, all of these authors found not only that Arcadia Planitia is rich in ground ice, but such ground ice would be excess ice. And here I put a short glossary for those of you who are not familiar with this terminology. So let's see a few things. Permafrost, first of all, it's a perennially frozen ground. So the temperature is never greater than 0 degrees Celsius. And ice within permafrost can occur in different forms. The ones that we're more interested in are the pore ice and excess ice. So pore ice is a volume of ice filling the pore space in a matrix. And it can be filling this space in variable percentages. On the other hand, excess ice is a volume of ice exceeding the total pore volume that the ground would have if not frozen. So there is a huge difference. You can imagine extracting pore ice and extracting from a pure sheet of excess ice. So the extraction would be much more efficient. You will get more ice, and it would be also pure. So all the authors that I said before found evidence for excess ice, which is great. It's really what we needed. And then on top of the system, we have a dry lag, which is basically a dry deposit that's protecting the buried ice from sublimation. Because as I said before, sublimation on Mars is really strong. And we're happy to know that this ice is protected from the dry lag. Now I will show you just a few highlights of our project in Arcadia Planitia, and we focus on geomorphological evidence for near-surface ice. There are in particular some periglacial and glacial features that can be considered a proxy for excess ice. The most widespread feature in the area is thermal contraction polygons. So these polygonal fractures form due to seasonal changes in temperature. So the temperature decreases, and at some point the tensile stress is exceeding the strength of the frozen ground. And to relieve this stress, we have the formation of these honeycomb networks of fractures. Now, here on the right, you have a sketch of a particular type of polygons. There are many types of polygons, but this is the type of polygons occurring in Arcadia Planitia. And you can see that there is a central part of the polygon, and then there are troughs, fractures dividing all the polygons. And below these fractures, below these cracks, some wedges develop. And they can be ice wedges or sand wedges based on the climatic conditions of the area. And there are many information that polygons can provide about the underlying ice. For example, by measuring their size, their diameter, we can infer how deep the ice is, because we know that the smaller the polygons, the shallower the ice, the larger the polygons, the deeper the ice. So basically what we did was to map thousands of polygons in the area, and we were able to extract some information on the possible depth of the ice. And another thing that you can infer just looking at these polygons is the maturity stage of the system. So if you measure the angles between these fractures, you can have an idea of how young or mature a system is, because at the beginning, the first fractures to form have right angles. And as the system develops and matures, these angles tend to increase. So we're going to have hexagons, pentagons in a more mature system. This is an example of polygons in Arcadia Planitia. So they give us also another very important information, because we see that the troughs between the polygons are very, very deep, while the central part is raised. So these types of polygons are called high-centered polygons, and they are a proxy for exercise. So I said before that from the diameter of the polygons, we can infer the depth of the ice. And that's thanks to Mellon et al., who developed a numerical model, basically an equation. So by measuring the diameter of the polygon in Antarctica, they came up with this equation, and they estimated the ice depth to be 10 centimeters. And of course, they had ground truth in Antarctica. They also had ground truth at the Phoenix landing sites, where the lander was able to excavate and find ice. And this ice was 6 centimeters deep. And the polygons were 3-5 meters deep. So you can see that these numbers are not fully consistent with the Antarctica numbers. And that's because Mars and Antarctica have totally different climatic conditions. So you cannot just, apply this model to any area. There are some things that you have to take into account, different climatic conditions, for instance. So we measured thousands of polygons, as I said before, in Arcadia, and we found that the diameter was quite constant, especially in the area, and it was around 11 meters. So we estimate the ice to be around 7-10 centimeters deep in Arcadia, which is super shallow and accessible. And it's what we wanted to know, right? So it's good news. Another important feature widespread in the area is expanded secondary craters. So here in this image, I put a primary crater that's occurring near one of these landing sites, and its secondary crater. So what happens is that you have the impact, the primary crater is formed, and the ejected material re-impacts the surface. And that's how a secondary crater is formed. And afterwards, all the secondary craters in the area show a highly degraded rim. And also the shape is elongated. It doesn't even seem a crater anymore. It's expanded and it's heavily degraded. And this is because of sublimation. So these expanded secondary craters are also considered a proxy for exercise. And another interesting thing about them is that some parts of the rim are preserved. And in every secondary crater, the only preserved part is the one located in the southwestern part of the crater, which is facing north, right? So the north-facing scarps are protected from sublimation, while the equator-facing scarps are all degraded. So this also gives us a lot of information about how sublimation works on Mars. And then, in this image, if you see carefully in the primary crater, there is also something called brain terrain. It's occurring on a terrace of this crater, but it's occurring also in other places, like here in this image on the right. So brain terrain is very widespread and common in Arcadia Planitia and also in other regions at the mid-latitudes of Mars. As the name suggests, it reminds of a brain because there is this anastomosing pattern of ridges and troughs, and it's been an enigma for many years. But recently, an analog was proposed for this feature, and it's the terrestrial vermicular ridge features that you can see here on the left. So they are, for certain, very similar, and vermicular ridge features are interpreted as the result of ablation of buried glacial ice. So this is, further confirmation that we're dealing with an area that lies on top of buried ice. And then, so there were also other features, but I tried to keep it short. And here is one of the geomorphic maps that I produced of one of the 3 landing sites. It's a geomorphic map, so we don't have any stratigraphic or chronostratigraphic information. We're just focusing on the geomorphology here because it's what we needed. I'm sure you learned during this week that based on what you need, you can produce a variety of maps. And they're so useful. They're really a powerful instrument because I can show this image to any planetary scientist, and just in a glimpse, they have an idea of what's occurring there, what types of features we have, and how extended they are. So I think preparing a map for any study area is really a powerful tool, and it's going to improve all of your works now that you have these tools as well. So I hope I kept it short enough. I have some take-home messages. So technology is advancing a lot, and it's bringing us closer and closer to having a human settlement on Mars. And we are the generation that needs to get involved. And I'm not saying that you need to go working as engineers for SpaceX and build rockets, but there are still many things that we don't know about these regions at the mid-latitudes. There are good candidates as landing sites. So any of us can contribute, because even the smallest contribution can help a great deal to understand many of the enigmatic features that we're still trying to constrain and characterize. And then, of course, in situ resource utilization is key. We cannot rely on Earth. We need a self-sustained settlement. So we need to prepare and characterize these resources in advance. And Arcadia Planitia seems to be the best candidate because it meets all the conditions. It's safe, it's flat, there's evidence for near surface ice, and it's located at the mid-latitudes. And yeah, maps are really important. So I hope that this week you learned all the tricks and tools. And if you have any questions, I'm happy to answer them. Thank you.